Welcome back. Today we continue our process of understanding and solving the renormalization group equations, right? So what we have seen is that by demanding that certain objects are independent of these renormalization scales that we introduced in our calculations, we can get differential equations for those objects, right? These scales were introduced during the regularization and the renormalization process, and we know they're not physical, right? And so in the last video, we looked at a particular set of renormalization group equations in which we choose this object to be the bare green function. So by demanding that the unrenormalized green function be independent of this renormalization scale, we got a set of equations which are called the Kalin-Zimanzik equations. And today we want to look at those equations, and specifically we want to calculate the beta and gamma functions for a few simple cases, right? The objective today is to get explicit leading order expressions to these beta and gamma functions, and to start developing some feeling, some understanding on what kind of physics these two functions encode, right? And in order to do that, we'll start with the massless lambda phi 4, right? For which we already derived the Kalin-Zimanzik equation in the last video, right? This is it, right? For any green function on this theory. This is a theory that only has one coupling, which is this lambda right here. And since we are taking massless fields, this is really the only coupling we are interested in, the only Wilson coefficient we are interested in, right? Keep in mind, we're assuming we're far away from the cutoff, so all these other irrelevant operators that could show up have all gone down to zero. We are working in 4 dimensions in this case, right? And we have already seen that the only marginal operator is lambda. All the other ones are irrelevant, and then you have the mass, but we're taking the mass to zero here, so we are in this, I would say, hyperplane where the mass is zero. The second point is that we can, in this case and for leading order calculations, actually use the Kalin-Zimanzik equations themselves to calculate beta and gamma, right? And the reason we can do that is that while this looks like one differential equation, is really a system of coupled differential equations. You can see that that happens for 2 reasons here. One is that we have this free n here, which is the number of external legs for this green function, which is free. So I have at least one equation for each value of n in which the green function is different from 0. We know that in the case of lambda phi 4, that only happens for the even number of external legs, right? All the odd green functions are 0 for this theory, but that still gives us an infinite number of differential equations. And beta and gamma are the same for all of them. So that couples all these equations, and we can use that. The second point is a little less obvious, is that we are also assuming we are well within the perturbative region. And that means that these 3 terms that show up in the equation here are really polynomials, right, in the coupling constant, right? I can expand all of these guys as polynomials in this coupling constant. This is the true also for this guy and this one, right? And so I get a set of equations for that for each power of lambda, right? So I have some coefficient of lambda 0 that gives me one equation for this order. I have another one which gives me another equation, right? And this is a very useful trick that we use again and again during today's video, right? And that's very useful because sometimes, even if I don't know some object here, still I didn't solve for that object, I know at which order it starts receiving contributions, right? So we know that there's no running at 3 levels. So that tells us something about these functions that are intrinsically connected to loops, right? And then I can get much simpler equations, at least on these very first orders in lambda, right? Eventually, I always have these 3 terms different from 0 if I go high enough in this expansion, but the very first terms maybe allow me to, we'll see, right? But maybe I'll be able to decouple a few of these terms and solve for beta and gamma before I try to solve for G, which is our final objective here, is really to solve for the running of the green function. But there is this trick that it's possible for perturbative theories, right? And that's what we're doing at first. So let us start by the 2-point function for lambda phi 4, right? These are the very first contributions to the 2-point function. It's important at this point to remember that now we're back to calculating green functions, because we spent so many videos already calculating only 1PI functions, right? That is easy to forget that now we are including these external legs, right? They are part of the green functions. They are not part of the 1PI contributions here, right? Or the amputated contributions that we were talking a lot in the recent videos, right? So now we're looking at the full thing. The only thing we're excluding here is disconnected diagrams, which do not contribute to anything relevant, right? So now we want to look at the behavior of these functions in terms of this perturbative expansion, right? So we know this guy is the 3-level contribution, right? It's not it's a 0 order in the coupling constants. These 2 guys, this loop and the counter term, are order lambda. And then I have this very first contribution of order lambda square, but I have other contributions, right? I have, for instance, the 1PR contribution, which is just 2 insertions side by side of this loop, and a few others, right? Also a loop with the counter term. Right? I don't need to look in details at this order, because this is what will matter most to me, right? And the important point here is that we already calculated this loop, right? And we have concluded that this guy does not contribute to the delta z part of the counter term. It only corrects the delta m square part, right? And that means that when we are setting our renormalization conditions so that the physical mass is 0, this guy will conceal exactly this one, right? Because there's no momentum in this limit of 0 mass, there's no momentum dependence on this guy, right? At least not a log dependence on the momentum. And that means I can eliminate it completely by setting a counter term. This is always 0. And there's no correction to the thing I want to look, which is delta z. Another way of seeing this is that I can set a condition. Remember that our renormalization condition is to set some combination of the external momentum, in this case just p square, equal to minus m square. If you go and look at the analytical expression for this guy in this limit where the physical mass goes to 0, there's no dependency on p square. So this whole term won't depend on m square, and that means that when I do these derivatives, they'll go to 0 and won't contribute to anything I want to look at the Kalan-Zimanzik equation. In other words, let me copy the equation here. This means that this equation for G equal to, let me remove all of this, right? I don't want to be carrying too much notation. And here we have a 2, right? And that means that at order lambda, G2 is not changed at all, right? These 2 terms will just conceal each other, right? And you get essentially the free theory propagator, which does not depend on any renormalization constant, and neither does it depend on lambda. So at order lambda, this is 0, right? And this is 0 because this is the derivative in the coupling, which only appears in G2 at order lambda square. And then you get a very simple equation, which tells me that this guy needs also, right? So if this is 0 and this is 0, this guy needs also to be 0 at order lambda. And of course, these guys are connected to renormalization, so they are also 0 in the free theory. Right? And so the conclusion is that, and let me write this explicitly here, is that gamma of lambda is an object that starts at order lambda square. This is really important because now I have decoupled lambda from the order lambda equations for all green functions, right? Gamma is the same for all Kalan-Zimanzik equations independently of the number of external legs, right? Now I can use this in another equation for a bigger, right, more green functions of higher order, right, with more external legs. Let's do that, right? So let's save this result and go to the next simplest green function, which is the 4-point green function. So let me paste the Kalan-Zimanzik equation again. Now I want to go to a different one. Let's go to G4, which changes these two numbers, right? So now that's the Kalan-Zimanzik equation for G4. In this case, the contributions are these, right? So we have a 3-level contribution, this one, and the one loop contributions here, the first counter term, and then higher 2 loop or more contributions. Right? Again, we want to do this analysis of the perturbative expansion. So this guy is order lambda to the power 1, right? Everyone here is at least of order lambda square. Remember, the counter term can have higher orders of lambda to conceal even divergences that come from higher order loops. But these 3 guys are order lambda square, right? Which can be readily seen here, right? Just have 2 powers of lambda. And of course you have order, in this case, order lambda cubed contributions and higher, right? What I am excluding here, you can see that I'm putting these diagrams minus a particular set of contributions, right? Because I could have other lambda square contributions of this form, right? I could get and put an extra coupling here and an extra loop, an extra loop in this way, right? Same thing I could have done, for instance, in these guys here, right? And put some extra terms like this. Or even, something like that, right? And the reason I'm not putting all these external legs, again, is that I'm interested at these at leading order. And you can see that these diagrams fall into pitfalls, right? This one and this one, we know that this guy does not contribute to delta z, right? So delta z is 0 in both of these cases, right? And that means, again, they don't cause any change in G4. They could cause a change in the mass, but in this theory, I'm keeping the mass at 0, so these will conceal exactly with some other diagram in which there's a counter term here, right? And the cancellation will be exact between those, right? And these two also, this one on the flip side, right? This guy wouldn't have delta z equal to 0, because these actually, we have seen that before, that at order lambda square, we didn't calculate this explicitly, but I have said that if you go to higher order in the propagator correction, then you get contributions to delta z. But on the flip side, and that's true for this one too, these are order lambda cubed already, right? You have 3 So in this case, if I'm stopping my equation at order lambda square, all these corrections to the external legs do not contribute, right? So again, I'm not forgetting the external legs in G4. It's just that at this order, I don't have to worry about them yet, right? You'll see that eventually we'll worry for another calculation, right? So with that in mind, I can do the same thing I did before, right? I can look at the contributions of this guy and see how the counter term depends on m squared to use that in this equation, right? So let's write G4. G4, again, depends on 4 positions. I'm not writing all of them. Actually, I'm interested in looking at these guys at position in momentum space. So all these green functions are, I'm calculating them in momentum space. So it could have 4 momenta here, but I'm suppressing that notation. And so the very first term is just minus I lambda. Then you have each of these 3 contributions. We have calculated that before, right? I'll put a link to the video, but we call these gamma loop, right? It's a gamma loop. And we have seen that they have the same expression, just exchanging which momentum is running here. So there's one for the S channel. So the momentum running through the loop is just the sum of these two. There's another one, but it's exactly the same analytical expression. I'm just making P squared equal to S, equal to T, and equal to U, right? In these 3 different diagrams, right? And then of course you have the counter term which we defined in this way. There's a delta lambda, we defined it with a minus sign here, so delta lambda needs to be equal to these guys at some reference point again, right? And then there's the sternal legs, right? I have to multiply these by these 4 propagators for the sternal legs, which in a massless theory look like this. So pi square here is each of these external momenta, and it runs from 1 to 4. You can just number them from 1 to 4. And I'm using the free propagator because of this argument, right? At this order, I really don't have to look at these loops. But if I want to worry about lambda cubed already, I would have this kind of contribution, right, to worry about. So this is the expression I want to look at. And now I have to, in order to plug this into the Kalan-Zimanzik equation, I have to decide on my renormalization scale, right? As I have shown in the previous video, it's not too important which choice exactly you make here, but we are sticking to our to one scheme, which is to take every combination, right, of external momenta, right, every invariant, right, that I can construct from external momenta and setting it to minus m squared. That puts us in what is called the Euclidean region. These functions are all real in that region, and it's simpler to do it like that. And that's the variable for which we derive the Kalan-Zimanzik equations above, right? And so in that we have to adapt, right? We have already derived this counter term in previous videos, but for a different condition, right? In there, if I remember correctly, S0 was like 4m squared and the other 2 were 0, right? Now we're setting a different one, and that means we get a different counter term, right? In this case, the counter term will be the sum of these 3 guys calculated at these points, right? Which now are all the same, right? So this is just 3 times this gamma loop of minus m squared. And then we have to choose expression for gamma loop, because we calculated these both in Pauli-Wieler's and dimensional regularization, right? We'll use dimensional regularization here, right? And that means that delta lambda is equal to 3 lambda squared. Now I'm just taking the result we know from previous calculations, right? This is an integral in the Feynman parameters. And you had the usual expression for dimensional regularization, which is this 2 over epsilon, then a log, right, of mu square over something, but I'm bringing the mu square to the denominator here. It doesn't matter, right? Usually it's a plus mu square up there, right? And then you have this very well known to us by now function, which we call delta, right? Which is written like m squared plus x 1 minus x minus p squared, right? But now I have to calculate that at minus m squared, so that's how it looks. Also, I'm taking this to 0, right? I'm talking about the massless theory, so this is 0. I don't want to use it. And now you have these two unphysical scales, 3 if you count epsilon, but epsilon is a regulator, right? And of course there's other terms too. There's like logs of r pi. I don't care about those terms because they don't depend on any of these. Especially they don't depend on m, but they don't depend on any of these physical constants nor on any external moment, right? So these guys will contribute nothing, right? And they're also finite, right? The divergence is here. So now I don't have to worry about mu square anymore, right? Because we know there are logs of mu squares in these guys, right? And this condition will tells me, right, that because of this minus here, all the logs of mu will be concealed. So the whole G4 under this condition is independent of mu, right? The only dependence is on m squared. In any case, the equation, the Kalan-Zimanzik equation, was written for m, so the dependence on mu wouldn't change anything anyway. But I'm choosing a renormalization condition that eliminates mu as expected, right? Also, the 2 over epsilon goes away between these 3 terms and delta lambda, right? So the whole thing will depend, once I plug delta lambda here and sum, right? The whole thing will depend only on m squared, right? And particularly, it's easy to integrate on x now because it's just this integral of x 1 minus x here inside the log. We know how to do that, right? And so delta lambda, what matters for us is that our lambda is equal to 3 lambda squared over 2 4 pi squared 2 over epsilon minus this log of m squared plus a bunch of finite stuff that do not depend on m squared, right? And that's the important thing, right? Now I can calculate pieces of my Kalan-Zimanzik equation, right? You see, the only thing here, this is the equation, right? So I'm acting with this derivative on m on G4, and G4 is this, right? But the only thing here that depends on m squared is the counter term, right? That's where the dependency on my renormalization scale is entering my calculation. It's through the condition that forces this guy to some value. So this is the guy that depends on m squared. So the derivative in m acting on G will actually only act on this guy, make everything else 0, right? So all logs of mu, which cancel, by the way, but even if they didn't, the derivative will make them all 0, right? And so I can write that m, the derivative in m of G4, is equal to m, the derivative in m of minus I delta lambda, which is the part of G4, right? Is this piece right here that depends on the counter term times the propagators, but let me write them here. I goes from 1 to 4, I over pi squared, but the derivative is only acting on this guy. Everything else is constant, right? Let me try to make this a little prettier. That's an ugly 4 right here. So now I can just use this expression and do the derivative in m, right? This is just this derivative on this log is just 2 over m, right? And there's a minus sign here. So I have minus 2 over m is the result of this thing. M cancels with this m, and so you get 3. 3i. The minus is concealed by that minus, so 3i lambda square over 4 pi square. Because this factor 2 is concealed by this one, right? And of course the external propagators. So that's how the derivative of m on G4 looks like. So I got now explicit order. Of course, this is, keep in mind, order lambda square, right? It's the first order to which I have a contribution to this guy. It's the leading order. So that means I have to go back to my equation and use and try to figure out the Kalan-Zimanzik equation at order lambda square, right? So let's do that. Let me copy my equation down here again. So my conclusion this far is that this piece here, right, once I put G4 in, the whole thing, including G4, is order lambda square. Let's see about the rest, right? We have proven in the case of the 2-point function that this guy, let me change color, this guy is order lambda square, right? And we know that G4 is really starting at order lambda, right? If you look back here, right, let me rewrite it. So G4 is equal to minus I lambda plus stuff of order lambda square. Right? So G4 starts at order lambda. And then, of course, I should never forget the external legs, right? That means that del lambda now of G4, which is this piece right here, will be minus I plus something of order lambda, because I'll differentiate in lambda once, right? Times the external legs again. So now I can expand this equation and write. The first term is this. Then I have, right, this is m del m of G4. Then there is this piece, beta lambda, times this guy. Let me color it so you can follow, right? This guy, which is minus I plus something of order lambda, which I hope I convinced you of here, right? Again, times this. And then I have this piece, which is just 4 gamma of lambda, G4. And this should all equal 0. Now you see, this guy is order lambda square. This one starts at order lambda. And that means that this whole piece only starts at order lambda cube. Right? Now I want an equation at order lambda square. So I can forget this piece. Right? So that's the usefulness of what we did with the 2-point function, right? Green function, when we concluded this guy only starts at order lambda square. That means now I get a simpler equation for the 4-point green function at order lambda square. Right? And comparing these two pieces, now at order lambda square, they need to conceal in order to give us a 0 here, right? Otherwise, this guy is not 0 in general, right? There's nothing here that forces it to be 0. And since there is a piece here independent of lambda, that means that this guy must start at order lambda square. Otherwise, I cannot satisfy the Kalan-Zimanzik equation, right? There's no way this guy will be 0. This piece is already 0 at this order. Right? I can forget it at order lambda square. Right? And now I see this guy must start at order lambda square, and I can solve it, right? Because now, if it starts at order lambda square, that means that this piece is order lambda cube. I don't need to know it. And I can solve this equation that is left here easily, right? The equation I'm getting for order lambda square is just this one. There's a minus I here, minus I beta of lambda times the external propagators, external legs. This needs to be 0. And I can solve for beta of lambda, which is just this coefficient here, right? Just beta is 3 lambda square over 4 pi square, plus, of course, this is leading order contribution to lambda, right? It's the very first one, but you have higher order corrections, which you have to solve more loops if you want to get, right? So this is kind of nice because we're getting a lot out of it seems like nothing, but the fact is we have a very complicated system of equations with many equations, but at leading order you can kind of decouple, and without knowing gamma we already got beta, right? And that's an important result. Well, now that we do know beta, we can go back to the 2-point function and get gamma, right? So now I can go back to this equation, right? We know now that this guy here is order lambda square, right? Explicitly here, right? And that G2, right? G2 is something like a free propagator, let's call that just number A, right? Plus some function, let's call this F2 of M, which is order lambda square, because we have seen that order lambda corrections to this guy do not matter. They will cancel each other because the theory is massless, right? And then, of course, there's order lambda cubed contributions to this guy too. And that means now that these pieces, this piece and this piece, how do they look like, right? So for one, let me put it like this, right? The beta lambda times del lambda of G2 will be order lambda cube, right? Because this guy is lambda square, and the derivative acting on G2 will be order lambda. This will be 0, and you get a contribution of order lambda from here. So this is order lambda cube, and m del m of G2 will be this derivative in the mass, right? Will act on this function, which is the counter term, right? This is given by the counter term at order lambda square. If I actually calculate the lambda square loops. So this guy will basically come from this guy, right? There will be a divergence here. I have to change my counter term to conceal that divergence. That counter term will get a order lambda square contribution that is dependent on m, because I'll set my renormalization condition for that scale m. So this derivative in m will act on this guy, and that means that this is multiplied by order lambda square. So this contribution will be order lambda square. So now I can write my order lambda square equation, right? The first piece here will contribute, right? So I get a term that is lambda square times m del m of this function, right? So this derivative will act on all of these and will fish out this f of m, right? So this is the derivative that appears here. This piece does not contribute at this order because we concluded that it's order lambda cube. So I go straight to that one and write that this will be 2 gamma of lambda, right? And now there's a piece that is proportional to A, and there's a piece where I multiply gamma, right, with this other thing. But gamma is of order, at least order lambda square. We have concluded that before. And if I multiply that by this, will be order lambda to the 4th. So the only piece that contributes at order lambda square is really this A right here. So that's the Kalan-Zimanzik equation at this order, now that we know beta. Again, we didn't really need the expression for beta, only the knowledge that it starts at order lambda square. That already allows us to, combining with the knowledge we have from G2, to get an equation for gamma separately from the equation for beta, right? This I can solve. So gamma of lambda will be minus lambda square over 2a, right? I have to divide by 2a here. M del f2 of m del m. And of course, this is not an explicit expression for gamma, because I don't know f2. A is easy, it's just a free propagator, right? But f2 is not. In fact, A will be a coefficient, but we'll see pretty soon. But f2 is not, right? f2, I really need to calculate this loop, set the normalization condition, and find this contribution to the counter term, right? We won't do that here, but if you did it, it's not that complicated. You can just calculate that loop if you want. It's a good exercise, right? This is will give me a gamma of lambda, which is just lambda square over 12 times 4 pi square. So you can get an explicit expression for the gamma just looking at this particular loop, right? So with that result, we have calculated both the beta and the gamma function for lambda phi 4 at leading order, right? There's order lambda cubed, possible order lambda cubed corrections to both of these functions. You might be impressed with how simple a result we're getting from such a sophisticated calculation, right? Really, the information we are getting here is just this number 12, right? Once we concluded that gamma should start off at order lambda square, this part was guaranteed, right? And then you can very easily argue that these powers of lambda always come together with powers of 4 pi just by looking at the integrations you do, right? So really, we're doing this whole thing just to figure out this 1 over 12 factor here. Same goes for the beta function, right? There's also this lambda square over 4 pi square. So it's really a factor 3 that we did this whole calculation to figure it out, right? Of course, at leading order, these are quite simple results. And in order to put a finger on exactly where this information is coming from, let's try to do it a little in a little more abstract way, right? Or maybe a more general way, right? So just think of just a generic scalar theory, a massless scalar theory, because we don't want to deal with the mass yet, right? But which is not just lambda phi 4. It could have a more complicated interaction, right? I'm assuming it to be a relevant operator, so I can forget everything else. So if I take lambda phi 6, for instance, then I have to be in a number of dimensions where this is relevant. I'm not worried about these details. What I want to look at is how generically I can write these 2-point functions. So in this case, I'll have a propagator, right, which is I over p squared for the free propagator. In here, I'll have some loop, the very first loop that actually contributes to G2 in a way that makes G2 dependent on the renormalization scale, right? So this leading loop will have external leg leading to the loop, and then another external leg, right? And the leading loop itself will be something, if it contributes to G2, it means it needs to have a delta Z contribution, which means it's proportional to 1 to minus I p squared, right? It's the p squared dependent part that contributes to delta Z. And and you have some number, right? That once you're calculating the loops, you get some 1 over 12, some number, right? And then in dimensional regularization, you have a divergent part that looks like always 2 over epsilon plus the log of mu square, right? Which is that constant that fixes dimensions in dimensional regularization over minus p squared plus some finite terms, right? Logs of 4 pi, right? You name it. The important part is that these terms are independent of p squared and don't involve these constants, right? And then you have the counter term, of course. The counter term here, which again, there's an external leg, the counter term, and I'm again just worrying about the delta Z part, right? And I p squared. So I'm choosing here the leading loop that gives a contribution to this part I p squared, because then delta Z changes, right? That's the whole point. And then other stuff at higher orders. Right? So there are a few comments here. The first one is that in dimensional regularization, right, this 2 over epsilon divergent part always has the same coefficient, this thing I'm calling A here, of the log of mu square, because this log of mu square comes from the fact that eventually I have to fix the dimension of the integral outside the integral, right? And then I have a divergent integral that has something that looks like this, plus finite terms always, right? And once I do the expansion for epsilon near 0, that's where the log of mu square appear, right? And it's the product of the part of the log of this expansion that is proportional to epsilon times this that gives me this part, right? So A is sitting here all along, right? and so it's the same coefficient for both of these guys. Even more importantly, if you go away from dimensional regularization, this thing in other schemes would look like something, say polyvillars, it would look something like this, right? And so no matter what scheme you choose, and in this scheme I would call lambda my m, right? And then this guy would be some p0 that doesn't matter because it doesn't depend on m. I could do another thing here. I could just choose any number for this and choose mu to be m, right? All of these choices lead to the same thing, which is the log of this m squared that appears here has this coefficient a, which by the way is the same coefficient of the divergent part, right? So this guy seems to be really important. We'll see how much in a second, right? So now I can estimate the order of A, right? For one, this delta z here is the only thing that will depend on m. Once I impose my conditions, the dependency on m will appear here to eliminate mu, to do what it does, right? And that means that del g2 del m will act straight away on this guy and will be always, right? Just have to take all the powers of I here. This will be just minus I over p squared, the derivative in delta z, right? So delta z will be equal to this for some value of p squared, right? So delta z does not depend on p squared. And then the derivative in m will act on that expression. Right? As far as A goes, right? A, let's call whatever, I'm also assuming this theory has only one coupling. It could be a Yukawa coupling, it could be, I don't know, a 5-6 coupling, I'm calling that lambda. And I'm assuming this guy, and those couplings are contained here, and then they depend, of course, on what order this leading loop is generated, right? So let's just say this is order lambda to some power n, right? Here we will assume n is bigger than 2, right? Because we already seen that lambda phi 4 is one of the few theories we have looked at. At order lambda 1, it does not generate anything. You could try to cook up some theory where a leading loop contributes at order lambda to the power 1, but I don't know any relevant theory that it does, right? So let's assume, just for the sake of the argument, that this leading loop is at least at order lambda squared, right? If you assume that, then G2 will be again some constant plus order lambda n, right? And del G2 del lambda will be of order lambda n minus 1, right? All of this is what I need to now construct my Kalan-Zimanzik equation and see what we can extract from it, right? Let's see. So now let me write the Kalan-Zimanzik equation. Del m g2 plus beta lambda del lambda g2 plus 2 gamma of lambda g2. And now let's see how the perturbative expansion is working here, right? So as I said, G2 is some constant plus order lambda n. This guy is at least order lambda. There's no way around it, right? And this one, I conclude that this is order lambda n minus 1, right? And that means this thing is at least order lambda n. And this guy, right? This guy is at least order lambda, which means that order lambda times constant here, that this whole piece is at least order lambda, which means that if n is bigger than 2, this piece with the beta function always enter later than this one. So I can take this equation at order lambda and ignore the beta function. That's what we did, right, at first. And in the first calculation we did, we ignored this part and this one and figured out the order for gamma. More generally, I can only ignore this piece, right, and say that. Now I'll just repeat this part using this, right? So I can write that, I'll just plug this piece right here, right? It's just an extra power of m, so I can write this as minus I. You cannot see it over there, but let me copy it down here. My face is in the way, so I can put this in here. M, oops, m del m delta z plus this piece to gamma lambda, and P2, the constant is just I over P squared, right? It's the free propagator, right? And this needs to be 0. So this is true in general if you're only looking at the leading correction for gamma, right? This is not the full expression to gamma, right? So this is gamma at leading order. We can solve for it. Half of m del m of delta z. So you see that the leading contribution, let me put up something like that so we do not forget that this is not exact. This is not an exact solution for gamma, but at least at leading order, you see that the contribution for gamma comes from the counter term for the normalization of the propagator of this particle. Remember, delta z is the part that corrects the residue of these propagators, right? It's the field renormalization constant. Now we can figure out delta z in general, right? If you go back to this equation, right, you see that delta z needs to be equal to this for some condition. Let's copy this. I'll just write again, right? So what we have from that condition is that I p squared times minus I p squared a, the all important a, 2 over epsilon plus the log of mu squared over minus p squared plus some finite terms, I will not write them all the time, I over p squared plus I over p squared, I p squared delta z, I over p squared, needs to be 0 at some point, right? At some renormalization scale, right? If I just put this in here, right, and solve for delta z, it's very easy to do because everything here is the same, right? And I get that delta z is just a times this calculated here, right? Plus, if I also want to eliminate these extra terms with this condition, I need to, right? So there's also the finite terms, right? But they don't matter, because now if I plug these in here, only the part that is dependent on m, that means only this log of 1 over m squared, really matters, right? And I get a gamma that is, let me just copy that, half m. And then the derivative will be just, let's not forget a, right? And the derivative of the log, since the m squared is down here, is just minus 2 over m, right? And that means gamma is minus a, right? And you see now why we get such a simple expression, right? All you're really looking for is, after you do the integration, this thing that multiplies the divergent part, because that's the same thing that multiplies the log of this renormalization scale, and is the same thing that multiplies the log of minus p squared. And that's because of these relations that we alluded to in the last video between the log of these external momenta and the log of these artificial scales that we put in order for in the ultra-relativistic limit to have logs that have the right dimension, right? So you see, in the case of gamma, what you're fishing for with all this complicated procedure, right? Now let's try to make this a little bit more general. Now I want to calculate a green function with n external legs, right? And I'm assuming there is some interaction with coupling that I'll call now G, that connects all these n external legs in a point. So that defines an interaction. But now I'm assuming these external legs are not all identical. They are still all massless scalars, but suppose there's some quantum number, some other interaction, not this one, that allows me to differentiate these guys. So this product over the external legs, so this green function can in general be written as the corrections to the vertex, to this vertex, right? So this is the vertex itself, the loop corrections, and the counter term to the vertex. And you have to multiply these by each of these external legs, which themselves have a free propagator, some loop corrections to this propagator, and some counter terms that correct these loops. But these external legs are not all the same, so I'll indicate that sum in a particular way. That is, right, the free propagator is the same for everyone, because they're all being massless scalars. There's no way to differentiate the free propagator. But the loop itself, I'll indicate like that. That's I over pi square, right, times that part that interests us, right? So you have some coefficient a here, which will now carry this index I, which can be different for each of those legs, and I'm making the product of all of them, right? And of course you have the log of mu square over the momenta that is going through that leg, right? Of course there's other things here, there's I times pi square here, right? So this, let me indicate like that, right? And then there is the counter term, which is just minus I pi square. There's a pi square to the right here too, times delta z I, because I'll have a delta z for each of these legs, and not all delta z's need to be the same. Right? That will change how we write the Kalan-Zimanzik equation. I'll show how in a second. But first I want to make this product of these vertex corrections by these propagator corrections. And I'm looking at this at one loop order. So I ignore all products that have loop squared, that includes loop here times loop here, and loop here times counter term there, and vice versa, right? Because the counter terms themselves only appear at the same order as these loops, right? So essentially I just have to take the 3-level contribution on the side, multiply by everything there, and the 3-level on this side and multiply by everything here. So the result for that will be that Gn at one loop order, right, will be first this guy multiplying everyone. This is the product from y to n I pi squared, because this thing is multiplying even these loop contributions, right? In fact, if I remove the I pi squared here, I can remove this guy, right? Because they cancel each other perfectly, and then the equation is something like that plus the finite part, right? And now I have this vertex, which gives me a minus ig. This loop, for which I'll make another constant like a, right? So when I figure out the integrals for this loop calculation, I'll get again some numeric constants, which you can guess will be important. I'll call that b. And of course, I have to do regularization for that loop, assuming it's divergent, and that will give me some well-known expression, right? So I have again a 2 over epsilon, some log of mu over minus p squared, right? And then there's this counter term minus I, and I call the delta term delta G. Let me put that in yellow, right? And that's basically this free propagator times everything on that side. Right? Now, if I have to do the opposite, right? So take this 3-level contribution there, which is minus Ig, right? If I multiply by everything on this side, the very first term is already out there, right? It's just minus Ig times this full propagator, the free propagator, right? And then I can make this thing times this one, right? Again, I put the I pi squared outside, right? This product of I pi squared outside. And then I have here a sum, right? Because I'll just make these multiplying each of these terms in this product, right? So that becomes a sum of AI times 2 over epsilon plus log mu square minus pi square. And the difference between this pi is the momentum going through each of these propagators, and this p square here is some combination. It's the total momentum going through that loop, and that depends a lot on how these legs are connected inside here, right? So I can build a bunch of Mandelstam-like combinations of momentum here, and in the end we know we'll set everything, every one of these contributions to m squared, right? And then I can add them all up, right? And that's where B comes from. B is actually the sum of all possible ways of going from this initial to this final state. So you can have S, T, and U channel, but now with more external legs, there's more combinations, right? But once I set every single of these Mandelstam-like invariants to m squared, I can sum all of them and have just one B for everyone, right? Which is the result of that sum. So let me just finish here, and then I have this delta Z I, right? Also within that sum, let me put this sum like that, right? And again, these factors of I over pi squared are all in front there, right? And there are, of course, terms with more loops. And that's our expression right here, right? So now I can use that to write the Kalan-Zimanzik equation, right? Keep in mind that eventually I'll make all momenta, all invariants that show here of momenta equal to minus m squared, right? Actually this way, right? And that sets the condition for delta G. And in the propagators, I'll do the same, setting each of these momenta individually so that I fix delta Zi, right? In the Kalan-Zimanzik equation that we have written so far, you had just one field always, right? So you had something like that, right? Del m del del m plus a beta function of g. Now I'm exchanging lambda for g, so it would be something like that, del del g, right? And some n gamma g, right? Because you had only one gamma and a number of external legs, right? Now I'll change that, right? So we have also shown that our n gamma g, right, was 1 over 2 m del m of delta z, right? Now I'll have something that looks like the number of legs for a particular some ni gamma I, right, summed over I, right, all the way to n legs. So that this tells me that you have, I don't know, n legs of the type of particle I, which has a gamma I, which is now proportional, right, to Zi, because I have many different species of particles. If I substitute that here, right, this one becomes just half m del m of delta Zi. Right? You can easily convince yourself that you generalize. The way you get n gamma n is just seeing how a green function with n external legs transforms. If you have different kinds of external legs, you have to sum over these different transformations, right? And all of that is actually acting on G and P, right? And then this needs to be 0. Now, I can use these expressions up here, right? And remember that these things in yellow here are the only two objects that will depend on m, right? Once I set the renormalization condition, delta G will be dependent on m, delta Z will be dependent on m, and nothing else, right? And that means that now I can substitute this G here by this big expression and rewrite my equation in the following way, right? So this guy goes through, it's a common factor to everyone, right? Then I have, I put a big bracket because this is, can be complicated, m del m, this first term here. I only really have to worry about the yellow part, so this will be minus I delta G. There's a minus here, so with this minus is plus I G, the sum from I to n of delta Zi. So this is what this first term contributes. I have beta G del Gn del G. Right? And then this thing, just copy it down here, Gn, and this needs to be 0, right? Now I can do my perturbative expansion analysis as usual. This thing does not matter, right? It's not zero in general, so the equation really demands that the thing in brackets here is zero. Delta G starts at order G, right? Capital G starts at order small g, as you can see here, right? That means that the derivative will be minus I plus something of order g bigger than 1, right? That depends on the details of the theory. Same thing here, right? This guy starts at order minus ig, so it starts at order g, plus something of order g bigger than 2, right? G to the power bigger than 2. Right? We don't know at first, right, if this contribution coming from delta G or the contribution that is effectively G times delta Z kicks in first, right? That depends on what loops, what the one loop, maybe the one loop contribution in this theory will give me a delta Z which is 0. Maybe the delta G at one loop is 0. We don't know. We don't know which of these kicks in first, right? But whatever one it is, we need beta here to conceal it in order to get a zero equation, because this other contribution, which is essentially the gamma function, is already multiplied by a higher power of g than beta is. You see? The lowest contribution here we'll have to conceal with g, because this is entering later, right? And that means that beta of g needs to start at the same order as delta g or delta g, delta z, whatever comes first, right? So we can ignore this part and we can ignore this part. Everything is really coming from the lowest order here and the lowest one there, right? So let's write everything with that in mind, right? Now I don't have to worry about this. I can write m del m minus I delta g plus I g sum delta zi. Remember, this sum is over I. Now I'm using this part, so I have minus I beta of g. And then this part, which is minus ig sum I equal 1 and half m del m delta. This looks like a 2, but it's just a partial derivative. Delta zi. And that needs to be 0. Now, I can use that to solve for beta. Right? Essentially using already the answer I know for gamma here, right? And write beta g equal to m del m minus delta g plus half of g sum I to n delta z. Right? The important step here is that you convince yourself, because there's no powers of g here, right? And this guy is a least order g, which is the same here, right? Then this enters at the same order that the lowest of these guys enter, right? Either delta g or g delta z, right? G delta z. So this is the expression for beta. And let's put a box around it. Right? And now we can look at the renormalization conditions that we have been using and figure out delta g and delta z. It's not hard, right? We did that a a bunch of times, you can go back and look at the expression. It's just that delta G needs to be minus B 2 over epsilon plus log of mu square over m square, the usual thing, right? That plus finite terms, right? That will conceal the thing that comes from the loop. And again, I have these constants here, right? That gives me a cancellation between this term and this one. The way I define here, they have the same sign, so that's why delta G came out as minus B, right? And the same thing for delta Z here. It needs to be essentially this for pi equal to m minus m squared, right? So now delta Zi is AI times very similar expression plus this, right? And this number, of course, changes depending on my scheme of renormalization, but it doesn't matter, you see, as long as I have this same thing, right? All these finite parts are not m dependent, right? These and these, right? So now if I plug that over there, I can act with the del m in these logs. It's the usual minus 2 over m, right? Which means this factor of 2 goes away. In here it doesn't, right? So my beta function of g will be minus 2b minus g sum of ai, right? So you see, in general, of course, you would have to see which of these guys is non-zero at a particular order in G, right? I don't even know, I know for sure that this is just a leading order correction. I don't know even what is the power of the next order correction, right? It's power some power m, right? That depends on where these b's and a become different from zero. But you can see that in general, the beta function will receive contributions both from the correction of the vertex and the correction of the full propagators, right? The external legs will also contribute. But in any case, again, at leading order, the leading order contribution to beta will come from these coefficients of this common piece here, which is the divergent part. It would be some log of lambda in a Pauli-Villars approach, right? It's the same we got from the previous cases, right? And this is pretty general. You could reproduce exactly the same steps for a fermion, for a gauge boson. In the case of gauge boson, you have to be careful when you write the propagator for the gauge boson to eliminate that part that is eliminated by Ward-Takahashi identities and see what is the gauge dependent part. Some of these quantities become gauge dependent. We'll see pretty soon which one in the case of QED, right? But other than these very small details, you can do the same thing for a fermionic theory or a gauge boson, and the conclusions are the same. In fact, we can easily use this to calculate these functions for massless QED, right? We're still postponing the treatment of the mass, right? So in this case, we'll have two gammas, right? One that deals with the renormalization of the fermion field, the other one that deals with the normalization of the photon field, the electron and the photon, right? But you can show very similar expressions, one depending on the counter term for the 2-point function for the electron and the other one for the 2-point function for the photon, right? And that expression that we just show for the beta function, now becomes this, right? So the way we define the correction to the coupling constant in QED was in this way, right? We defined this delta 1 multiplying by the physical charge, right? And the renormalized charge, in fact, right? And so this piece becomes just minus E delta 1, right? And now you have to sum for the external legs. For beta function, you're thinking about this diagram, right? So you have to sum over two fermionic legs, each one of them, what we call delta Zi here, we call delta 2 in QED, and one for the photon line, in which what we are calling delta Zi was called delta 3, right? That's why it appears here and there, right? So because we have two fermion legs, you sum it twice, that half goes away, you get E delta 2, right? And since you have only one photon line, you have this half of E, right? G is our E, right? Delta 3. And then Ward-Takahashi identities kick in, right? We know that this delta 1 is equal to this delta 2, right? And again, you have this thing, right? We have seen before that the running of the charge only depended on the photon renormalization, right? This delta 3. And now we see that the beta function for this theory only also depends on this photon renormalization. We'll see that these two things, the running of the charge and the beta function, are related. But so far, this is just a consequence of the Ward-Takahashi identities, another one, right? We only need to know delta 3 to calculate the beta function. Now it's just a matter of knowing delta 1, delta 2, and delta 3. We can plug them here, here, and here, right? And calculate beta and gammas, right? It's not the same deltas we calculated before, because now we're changing our renormalization condition, right? That's why I cannot really call this the physical charge, because usually the physical charge we define for QED is for Q squared equal to 0, right? This is the charge defined at some higher scale, right? And we are doing the massless approximation here, so you also have to change that. So if you go back to our calculations of these guys, and instead of using the conditions we used there, you use these ones, right? That's another good exercise to see if you're being able to implement these conditions properly. You get this counter term for delta 3, right? This expression for delta 3, and this one for delta 2. And of course, delta 1 is equal to delta 2, so it's easier to do that for delta 2 because it's a simpler expression, right? But then it's equal to delta 1. And then it's just a matter of putting these guys in this expression. And this one, right? You're only differentiating in m, which turn these logs here into minus 2 over m. So it's just putting minus 2 over m in each of these places and multiplying. You see the beta function has an extra power of e here. So you end up with a beta that is proportional to e cubed, right? That's the leading order correction for QED. And gammas enter at order e squared. So see, in this case, gammas have a lower enter at a lower order in perturbation theory than beta, right? And again, all these functions, keep in mind, I don't want you to get confused by this. These all are leading order corrections, so there are higher powers of these higher order corrections to this initial value, right? Another thing to keep in mind is that some of these results are gauge dependent, right? These are not observables. These functions are not observables. In fact, we have to go back with these alpha, gammas and betas to the Kalan-Zimanzik equation to calculate green functions, which are also not observables, right? So a lot of things here can be gauge dependent. In particular for QED, we know that this is the contribution, right, where you have a photon propagator explicitly, because when you're calculating delta 3, you only involve the fermion propagators. So delta 2 depends on the gauge you use, right? And by consequence, since they're the same, right, delta 1 also depends on it, right? But delta 3 doesn't. And that means that the beta function is not gauge dependent either, right? Only the things that depend on delta 1 and delta 2 will depend on the gauge you choose, right? But you have to do that consistently everywhere, right? So there will be other gauge dependencies in your calculation, and they should all cancel out if you go towards observables, of course. As a final point for this video, which is already getting too long, let's take another look at the definition of beta and gamma and try to write it in a way that is more transparent for what they are doing, what kind of information they are conveying about your theory, right? So we have specified, again I use lambda phi 4, a scalar theory, in fact, just because it's easier, but this calculation I'm about to do is, it's easy to apply to any field theory, right? So we have defined a renormalized field, right, which is some function, I say, if I stay in momentum space, it's a function of p, right, which is defined in terms of a bare field through this field strength renormalization, which now we know it will be a function of m, because eventually I have to choose some renormalization condition which will specify parts of this function right here, right? And then I asked myself, that's how I got the Kalman-Zimanzik equations, right? And the definitions of alpha, of beta and gamma, right? I asked myself, how did these objects change when I change this renormalization scale, right? And I define a variation of the field in this way, right? When this happens, the renormalized field goes from phi to phi plus delta eta phi, right? And that means that some phi prime, which I can call this phi prime, right, will be 1 plus delta eta phi, right? And I can now write this some phi prime as using this expression, right, as z to the minus half calculated at m plus delta m, right, of phi 0. So this is the point in which I'm calculating z, right? And the original phi was the same, but z to the minus half, right, was calculated at the point m times phi 0, right? I'm writing these two fields, one defined at the point m and the other one defined at m plus delta m, both in terms of the bare field. Now I can divide these two, right? If I do it on this side, right, phi prime over phi, I just throw this phi to this other side here, right? That's 1 plus, so let me write it like this. Phi prime over phi, right, can be written using this equation as 1 plus delta eta, right, here. And using this expression, I can divide these two things, right? This will be z at m plus delta m over z to the minus half of m. Of course, I have phi 0 here, and those go away, right? So now I found a relation between the theory defined at m and m plus delta m. Now this is easy to isolate, right? I can write delta eta in terms of this, right? I just take this equation, write it like that, right? Minus 1. And then I can go to the definition of gamma that we had, right? So this is the important thing that I needed here. I want to exchange. I had a definition of gamma in terms of this delta eta. Now I want to write it in terms of z, which is a more interpretable thing for us. We know that z changes the normalization of the field. So let's do that, right? I can write my original definition of gamma, which was just m delta eta, right? Where delta here is the transformations everyone undergoes when I change m in this way, right? So now I want to write this like that, right? But I'll just take the z to the power half and distribute here. So I get z to the minus half m. This one repeats here. This one is here, right? That's the minus 1. And now I'm getting something that looks a lot like a derivative, right? I just have to replace this guy out here, and this one goes in there. And then I take the limit, right? And then I take the limit. Let me make these a little bit smaller. I take the limit where all these deltas are really small, right? That becomes just half, because I have this minus half up here, right? This is just this guy. Let me write it explicitly. This guy, when I take that limit, that's just the partial derivative in m of z to the minus half. I can take that derivative, and then that's the half that comes out. There was a minus here. With this minus is just half of m over z to the minus half, right? Z minus 3/2, because I did this derivative, right? Del z del m, right? Which means now that I can simplify the z's here and rewrite gamma as half of m over z del z del m, which is a more useful definition of gamma, right? Because it's easier to get z and just do these derivatives, right? And also you will notice, right, that we up here, let me find it, when we were doing the general thing here, we got an expression for gamma that was this, right? Del m of delta z, right? Plus corrections. This is valid at leading order. The one we got now is valid at all orders, right? This one is valid at all orders, but it reduces to that other one in the limit of at leading order, right? Because you can write z equal 1 plus delta z, right? And then this thing will be something like you can write that as a power series, right? You can write z here, right? Will be this 1 plus minus, in fact, because I have a plus here, to the numerator will be minus delta z plus some order delta z square, right? That's what happens to the z in the numerator, in the denominator here. And this guy will be just delta z del m, right? So you see that at leading order, this one here, right? This is really half of m over del z, right? So it reduces to the previous one, but now we have a definition for gamma that is valid at all orders. And more, it shows us now pretty directly, right? That gamma is directly tied to the field strength normalization, right? It tells me how the normalization of the field changes when I change the scale, right? It's kind of a running for the field strength. Of course, when we talk about renormalization group equations, the normalization of the propagator will be set to 1, right? So this, but then when you do that, this change in z will go to other Wilson coefficients, right? So that tells me how z is changing, and that will influence all these other Wilson coefficients, right? The definition for beta, if you want to do the same for beta, is a lot more straightforward, right? Because we define beta already in a pretty explicit way of what it is. So we define it in this way, right? Delta lambda. Again, when delta m is exactly the same we had here, right? And that's a lot easier to turn into a derivative, right? Because we had m going to m delta m, right? And when that happens, lambda of m plus delta m is lambda of m plus a delta lambda. If we substitute that up here, right, that immediately becomes m delta m. And this guy I can just rewrite as lambda of, sometimes Portuguese slips out, lambda of m plus delta m minus lambda of m, right? And that's straight out when I take the limit, right? That's very straightforwardly the derivative. So that's m del lambda of m del m, which tells me how this coupling, let me pull that out, because that's, again, a very good definition of beta, right? And it shows me, this one we usually use it the other way, right? If I know beta and I solve for this differential equation, I'll find out how lambda changes when I change the scale of my theory. This is sort of the running of the coupling constant. I'm seeing how the coupling constant changes when I change this non-physical scale, right? But we know that this non-physical scale comes in a log with the external momentum, so it's already, you can glimpse that we will be able to connect these running in terms of this artificial scale to the running with the momentum, right? The external momentum. But we'll see that in the next videos, right? For now, all you have to see is that beta is really directly connected to the change of the coupling constant of the theory. And then you understand something we have just shown, right? Which is that the beta of QED is only dependent on delta 3. And we have seen that the running of the electric charge is only receiving contributions from the self-energy of the photon. And again, the beta function is the same. Not by chance. This is guaranteed by the Ward-Takahashi identities, like it was before, right? When we got to the running of the coupling constant in a completely different way, right? So you see that all I need to know in order to get the running of the electric charge is really this beta function, but that's a subject for the next videos. See you then.